Hello and welcome back for another VMK in the game development series. This VMK is going to focus on adding text to our game engine. Okay, let's talk about fonts. Before I jump into the code on how to implement fonts in our game engine, we should get an understanding of what fonts are and what kind of things are associated with them. To do this, we can go to Wikipedia and type in typeface. You should find the following page. When you read through this document, you'll get a better appreciation for what's involved in any specific font. Now, in our font engine, what we're going to be doing is we're going to be implementing a textured-based font. What this means is that when you ship your game, you'll be basically shipping images that contain all the fonts that your game uses. There's many different ways to implement fonts, but I found that implementing texture fonts is sort of the most secure way because you're guaranteed that your fonts are actually going to look exactly the same way on your customer's computer as they do on your computer. And the reason for that is because you're using textures to represent your fonts. You're not actually using Windows fonts to generate fonts in your game while it's running. So let's talk a little bit about fonts themselves. There's two major types of fonts. There's proportional fonts and then there's monospace fonts. Proportional fonts mean that the letters within the font are proportional, so W's and M's will be really wide, whereas L's and I's will be narrow. And when you print out a word in proportional font, everything gets sort of squished in together as close as possible to one another. With monospace font, all the letters are given the same amount of space, so everything is spaced out equally. You'll find that in regular written text, proportional font is used a lot more. Monospace used to be used whenever typewriters were around because typewriters didn't really have a way to proportionally space out letters. They all had a casted image of a letter on a key, and each of those keys were the exact same size. So a typewriter worked in monospace. Now, the font engine that I'm going to show you how to create will actually incorporate both. We'll start off with monospace because monospace is actually the easiest to implement. And then in the next VMK, we'll go through and modify the code slightly so that we can create proportional fonts as well. And you'll notice that the amount of work to get proportional working is a little bit more, but it's definitely worth your effort because it looks a lot better and you save a lot of space on your screen. Monospace fonts aren't all that great for computer games because if you have a lot of text, the text will take up a lot of space on your screen. So have a read through here. When working with proportional fonts, we'll be talking about baseline, so make sure you understand what a baseline is. Referring to this diagram here, baseline represents the bottom line here that our text sits on. So you get hanging letters, which go below the baseline, and then capitals and regular letters sit on top of the baseline. Each font that you use will probably have a different descending height as well as ascending height. These two numbers are variable depending on the font that you choose to use. Okay, so that's about all I wanted to say about fonts. Now let's go into our code and get started in terms of the implementation. To get the font engine up and running, it's going to be a little bit of work, so I've broken up these VMKs into another mini-series. I think it should be around 3 VMKs. The first one, we're going to create the main font.cpp and font.h files. In the second VMK, we're going to implement the monospace work, and then in the third VMK, we're going to implement the proportional spacing. And of course, we'll also have some testing in there to show you the fonts up and running. So let's get started with the font class. Going into our Solution Explorer here, let's minimize some of these groupings. And we're going to add our font class into our scene library. So let's select Scene Library, and I'm sure you've done this many times already. We'll add a new item. I'll add the CPP, and I'll call it Font. And then we'll repeat that for the .h as well. Inside the .h file, let's add the following code. At the top, we include core.h as well as color OpenGL.h. And then we have our font class. Our font class has a constructor which takes in a pointer to our error handler, graphics renderer, an unsigned integer, which is going to be a texture ID value, an unsigned integer for our texture size, an unsigned integer for our font size, and then a pointer to our font spacing. We have a destructor, and then we have a print text OpenGL function. This function takes in an x and y coordinate, as well as a color, a scaling factor, and then the text that we want to print to the screen. Under our private functions, we have build font OpenGL, and this just takes in one parameter, and that's the texture size. Down here at the bottom, we have some member variables. We have a boolean that specifies whether we're using monospace. If this is false, we're going to be using proportional spacing. We have some unsigned integers for our list base, as well as a texture ID, and another one for our font size. Lastly, we have our error handler pointer down here. I'll be talking about all this in detail in the CPP. So going to our CPP, let's take a look at our constructor. Okay, at the top we include our stdafx.h as well as font.h, and then we have our constructor. We set our member variable for our error handler to the value that gets passed into us, and we check to see whether the pointer here for our spacing is equal to null. If it is equal to null, then that means we're going to be using monospacing. If it's not null, then we're going to assume that we're going to be using proportional spacing, so we're going to set monospace to be false. We set the pointer value that gets passed into us into our member variable. If this is null, then our member variable becomes null. We save the font size here. The font size is a parameter that specifies how the font is going to look inside the texture file. I'll talk about this in the next VMK in detail, but for now just think of it as the number of pixels that each character inside the font can be. We initialize the list base value equal to 0 here, and the list base is used inside build font OpenGL, so I'll talk about this in a second. And then we also save the texture ID value that gets passed into our constructor into our member variable. So then depending on which renderer we're using, since we're starting off with OpenGL, we only have OpenGL as a case here, and inside here we just call build font OpenGL, and we pass into this the texture size. And texture size is also one of these parameters that gets passed into our constructor. Our destructor just cleans up any memory that gets allocated. So if this pointer here that gets passed to us inside the constructor here, if that value is null, then our destructor won't do anything because null gets assigned to our member variable, and down here we just skip over it. But if that value is not null, then we're going to go into here and call safe delete array to delete any of the memory that was allocated. The allocation of this memory, notice, is not done inside the constructor. It's not even done inside build font OpenGL. It's going to be done outside of this class, which is a little bit dangerous, but the way that we've structured the code, it has to be done this way. Okay, this next function, build font OpenGL, I've kind of cut up a little bit because I've taken out the work that deals with proportional fonts. Our initial work is just going to focus on monospace fonts, so you'll notice that there's going to be some things in build font OpenGL that are missing. We'll go and fill those in the next VMK whenever we talk about proportional fonts. But before I talk about build font OpenGL, I want to describe a little bit about how our texture font works. What we need to do is we create a texture, and our texture is going to be broken up into a grid pattern 10 characters wide by 10 characters tall. So it's going to actually contain 100 characters on the screen. Well, now when I say a character, I mean things like any alphabetic letter, lowercase, any alphabetic letter, uppercase, any digit, so 0 to 9, any exclamation point, any fancy character, basically anything you can type in on the keyboard, that has to go inside this texture. So let me show you what my specific texture looks like. I chose to use Impact Font. So our text is kind of bold looking and big, and I just picked that so that you can see it easily on the screen. You can choose any text you like. This texture here is exactly 512 by 512 pixels in size. Now remember, when you're working with textures inside our engine, it has to be square and it has to be in powers of 2 to the power of x, where x is any number. So I could have chosen this to be 128 by 128, 256 by 256. I just chose 512 by 512. I'll show you what kind of repercussions this has in the future. Now, I need to break this up into a 10 by 10 grid. The grid pattern that you see here is actually generated by drawing lines vertically every 25 pixels and horizontally every 50 pixels. So if you look here at the top left-hand corner, this square comprised of these two rectangles represent one cell. And I just did this so that I can see where the middle point of my cell is located. I need to know where the middle point is because for monospaced fonts, I need to specify all the character items to be centered inside of this 50 by 50 square. Now, the first square here is blank. It's actually the space character, so there isn't anything in it. Next, we have the exclamation point, double quotation, number sign, dollar sign, percent sign, and sign, single quotation, regular bracket, opening, regular bracket, closing. Then we have the star symbol, which is used for multiplication. We have plus, comma, minus, period. We have a forward slash, then the numbers from 0 all the way to 9. We have the full colon, we have the semicolon. Less than, we have the equal, we have greater than, question mark, the @ sign. Then we have all the capital letters, starting with the capital letter A, going all the way down to Z. We have the square bracket, which opens. We have backslash, then we have the square bracket that closes. We have the @ symbol, the underscore, another single quote. Then we have all the letters from A to Z in lowercase. Finally, we have the opening curly brace, we have the or symbol, and then we have the closing curly brace. And then lastly, we have a tilde. Then we have 1, 2, 3, 4, 5 blank spaces. These blank spaces could be used for anything. Now, on my keyboard, all these characters basically exhausted all the keys that I can press on the keyboard that generate some sort of output. There are F keys on my keyboard, but when you press an F key in a regular application, you don't see F1 appear on the screen. All the character items that you see on the screen are all the ones that you can press and have text output to the screen. Now, what's so important about the order that I've chosen here? Well, the order is actually very important because it's in the ASCII code order. Now, what do I mean by ASCII code? If you go to www.lookuptables.com, you'll find the following listing. Now, this listing gives you all the ASCII codes from 0 all the way to 127 in order. So, going from 0 and incrementing upward. And you'll notice that starting from 32 all the way down to 126 are all the characters that we're using. Here's a space, exclamation point, double quotations, and so on. So I've listed all of my items inside this texture in the same order that they appear here in the ASCII code table. Now this is very important because when we go and print text on the screen, we're going to be using a little trick which allows us to encapsulate our printing routine very, very easily. But for it to work, we have to specify our text in the same order that it appears in the ASCII table. I've highlighted here a couple characters. We have the comma, the semicolon, the underscore, the lowercase g, j, p, q, and y. These characters are highlighted because they're actually dangled below the baseline. Remember, the baseline is where all the characters sit on top when you write them out in a sentence. The comma, the semicolon, the underscore, and so on, they all sit below the baseline, or they have a portion of the character that sits below the baseline. You need to handle these special characters slightly different than all the other ones because they do lie below the baseline. Okay, so going back here, just remember all the characters have to be in the ASCII code table order, and they all have to occupy the same amount of space. Again, let me turn on the grid here. Notice that all the characters don't go outside of their box. The widest character we have is the capital letter W, and it just barely fits inside the region here, but it is perfectly still fitting. Thin characters like the or symbol or the letter I, the letter L, notice you have to position them directly in the center of the box. If they're not in the center, they're not going to work very well in the game engine. And for all those characters which I highlighted on the ASCII table, like semicolon, comma, where are they? The lowercase g, lowercase j, pq, and y, notice that they're actually lifted up. To make them fit inside this box, I couldn't make them in the same orientation that all the other letters are. So for instance, this Y, the top of the Y, should be even with the tops of all these other letters. But notice it's been shifted up so that the tail end of this Y fits inside its own box. If I didn't do this, then if I go and try to print the letter Y, it would have been chopped off. So you need to make sure that all the dangling letters are raised to fit inside the boxes that they're supposed to fit inside. Okay, so now you know what the file itself looks like. Now let's go take a look at the C++ code on how to deal with this texture. Inside build font OpenGL, we use glGenList to generate 100 lists. What a list is in OpenGL is a method to compile specific OpenGL calls into one listing. Then when you want to go and render something that's modular, you can just call that specific list and it'll call all the code which you compiled ahead of time. I'll show you how we do this for each of the characters. So I generate 100 lists so that I can store all the calls for every character. And then I create a couple temporary variables here. There's f_increment, which is the size of the font divided by the size of the texture. Now for us, going back here, the size of the font is 50 pixels because each of these squares here is 50 pixels in size. The size of this texture is 512 because that's the overall size of the texture. So this f incremental value is going to be 50 divided by 512. fx and fy are going to be temporary variables which we use to specify the texture coordinates within that texture that I just showed you. We start off by using a for loop that goes from 0 all the way to 100. So we're going to go through every single item inside that texture. And while we're going through there, we're going to extract the x and the y value. The x value is going to come from I modulo 10 times the increment value, which is stored up here. The y value is I divided by 10 times the increment value. So in other words, as we're going through this loop 100 times, fx is going to represent how far over horizontally we are, and the y is going to tell us how far up we are vertically. We then use glNewList to select one of these lists here that were generated. So initially, our list base is going to be 0, and then we're going to increment by the value inside our for loop. So initially, this is going to be 0, and then we're going to specify we want to compile a code. So between glNewList and glEndList, this is all the code that's going to get compiled. And what we're going to be compiling is basically the OpenGL function calls to render a rectangle on the screen, a textured rectangle. So what we're going to do is we're going to specify here the texture coordinates as well as the vertex coordinates for our rectangle. The s value for the texture coordinate is going to be equal to fx for the first guy, and the t-coordinate is going to be 1 minus the increment value minus fy. The vertex value here is going to be 0, 0. So we're going to choose the bottom left-hand corner of our texture. So let me go back into here and point this out. So the first item we're going to choose is this corner down here, the bottom left-hand corner of the first element cell. Then we're going to choose the next guy over here, and we're going to go up and then over. So for every single item we need to specify 1, 2, 3, 4 corners. 1, 2, 3, 4 corners. And we're just going to do this for every single item. As we're doing this, we're calculating exactly how wide we're moving over, how tall we are as well. And by doing this, we're also extracting the texture coordinate values for each of these coordinates here. So that's what this code here does. So the second guy is fx plus the increment, 1 minus the increment minus fy, and then we move over by the size of the font. Third value shown here, and we're going to move to the top right hand corner, so we move by the size of the font, and then we move across by the size of the font, and we move up by the size of font. And lastly, we get the top left hand corner, which shows you the texture coordinates here, and the vertex coordinates is just straight up by the font size. And remember, font size for us is going to be 50. Then after we do all this rendering for the textured square, we then need to go and move our current position by the size of the font. Since we're using monospaced fonts, we're going to move over 50 pixels. So what this does is it just takes the font size value, and we're not going to move in the Y, and we're not going to move in the Z. When we have proportional spacing, we're going to do some extra work down here, but for now I'm just leaving it blank since we're not going to worry about that. Okay, and the last function we're going to implement here is our print text OpenGL. So let's take a look at how this works. We pass into this function our x and y values, so this is the location on the screen where we want to start our text. We pass in the color that we want our text to be, and we also pass in a scaling factor and the text we want to print. So first thing we need to do is we enable textures, since we know that we're going to be printing a square that's textured. Then we need to bind the texture that uses the texture font. So we select our member variable here for texture ID. We then follow up by turning on transparencies, because as we're rendering things on the screen, we don't want to render this black portion here. We only want to be rendering the white text. Which also reminds me, I should tell you a key component of this texture here. What you're seeing here on the screen is not the full story. You need to make sure that when you generate these textures, you associate a mask with the texture. If we go under Layers, Load Mask from Alpha Channel, you'll notice here that the mask stored in this texture results in the following. The black portion doesn't actually exist. All of that has been masked out with an alpha value. The only portion that exists inside this texture is the font. So when you generate your font textures, make sure you only save the characters themselves and you mask everything else out. This is important because when we start going to render things on the screen, we may want to have, for instance, graphics in behind the text, and we don't want to have like a black box surrounding the text that we render in. If we do want to do that, we can do it as well, but it just makes it more versatile to have a nice masked texture like this. So make sure you do mask your textures. So since we do have a mask, we need to turn transparencies on, and we just specify the blending function here to be source alpha and 1 minus source alpha. We then select our model view matrix, set it to the identity value, and we move our position to be located at the x and y value that was passed into us. Then all the magic happens here. We call GL list base, which specifies the starting position inside our display list. Now notice that we take the list base value and we subtract 32 from it. The reason why we do this is because in the ASCII table here, let me turn this grid off. You'll notice that the space value is equal to 32. And in our display list, space was actually equal to 0 because that's where we started our display list. So we need to offset by this 32 value because we know we're never going to be rendering these following items on the screen, and we don't actually have these stored anywhere. We only stored from 32 on to 126. So we need to offset by 32 here, and then after we offset, we select the color that we want to render our text in. The color again was passed into us into one of these members. So we specify red, green, and blue values, and then before we render our text, we go and scale it using the scaling factor. So you can specify here a scaling factor. It's just a floating point number, and it's going to scale in the X and the Y direction proportionally. The Z isn't going to change anything because that's the depth of the text. Our text is actually flat, so there's no meaning to the depth. Finally, we call GL call lists, and we pass into it the length of our text that we're trying to print. We specify we're using bytes, and we pass in our text. Now what this is going to do is it's going to go extract the values here that we're passing in for the text, convert those to numbers, and using those numbers with this offset here 32, it then knows exactly which list that was generated up here in the build font OpenGL to call. So for instance, if for whatever reason you wanted to print ABCD, well, that's going to mean that you have 97, 98, 99, and 100 inside the texture array. We're going to subtract 32 from each of those values to get the new values, and those new values actually point to the display list values that was generated up here. Using those, it will then render all the items here that we specified and offset the position of the next text item. So as it goes through, it's going to go through, parse this entire text string, calling the lists numerically based on the text values and display them on the screen. As it's doing it, it automatically moves everything over horizontally for every character that it generates. Okay, let's compile our code to see if everything is okay. Oh, we got some error messages here. Oh, right. Inside font.h, I forgot to include the following member variable. So MPI spacing is going to be a pointer to integers, and we won't be using this whenever we're using monospacing, but we need this member variable whenever we're going to be working with proportional spaced font. So let's save that and try recompiling. Okay, so that looks like the only change we had to make.